Hi, I'm Brian Prier, tutoring high school physics. Today's topic, the work done by a gas and a heat engine. So here we have a particular setup where we have gas on the bottom and a piston on top. So what's going to happen is either you can expand the gas, increasing the volume and pushing the piston up, thereby doing work, or the piston can come down, compressing the gas, decreasing the volume, and doing work on the gas. You can measure the amount of work done from charts like these, where you have on the bottom volume in meters cubed and on the side pressure in pascals. If you don't already have those units, convert to those units, because that's going to be very useful in a second. So there's some special names for some of these processes. You'll notice from B to C that we have constant pressure of 4 pascals, while our volume is changing. If you see a process with constant pressure, then it's known as isobaric. Isobaric. We also have from C to A another type of change, which is very interesting. We have no volume change, but a pressure change. If you see no volume change, then the process is known as isovolumetric. So that's just handy to know. And now, on to calculating the work. Well, we could use the equation that work equals pressure times the change in volume, but that's only so useful. It's only capable of being used when the pressure is constant. So, from B to C, we have a constant pressure. We could use that equation to calculate the work. Not from C to A, because, well, for multiple reasons, actually. First of all, the pressure is changing. Second of all, there's no work being done. You'll notice that the volume is constant. No work happens if the volume is constant. Now, more usefully, from A to B, both the pressure and volume is changing, so work is being done, but we can't calculate it using this equation because our pressure is changing. So how do we calculate it? Well, in general, to calculate the work being done, just take the area underneath whatever line. So if we want to find the total work done by this entire thing, then we would have to take the area under A to B and also the area under C to B. So here's some rules about positives and negatives. If your volume is increasing, then the gas is doing work, so that's going to be positive. If your volume is decreasing, then your gas is not doing work. It's having work done on it, so it's a negative work. So I'm just going to say that the process goes from A to B, and then from B to C, and then from C to A. So why is this? This is because from A to B we have an increasing volume, and then from B to C we have a decreasing volume. It's just handy to define it that way. And so let's just see. So we're going to take the area under A to B and subtract the area from B to C, because the area from B to C is negative because your volume is decreasing, and that's negative work. And so we entirely cut out this section underneath the triangle because of that. A to B and B to C have that area in common, so all we're left with is the area of the triangle, which is pretty easy to calculate. A equals 1/2 base times height. So 1/2 times our base from B to C, that's 4 meters cubed to 3 meters cubed, so that's 1 meters cubed on the base. And the height from C to A, so that's 4 pascals to 5 pascals, so 1 pascal. And if we put this all together, we get 0.5, 1 times 1 times 1/2, and pascals times meters cubed, or remember, keep those units, is going to be joules. So pascals times meters cubed, joules. Convenient. You might also be asked to calculate the heat of a particular system, and you might want to know this equation, where the change in internal energy is equivalent to heat minus the work. So one handy tip, the change in internal energy of any particular closed system where all of your lines are connected is going to be 0. You might ask, what is actually the total internal energy? Well, the internal energy of a gas is basically all the chaotic energy that keeps the molecules whizzing about. Just a handy definition. No, but more importantly, you'll need it for this equation. So to calculate the heat for this particular system, we know that delta U is going to be 0. Our change in internal energy is 0, because this is a closed system, equals heat minus the work, which is 0.5. So we add 0.5 to both sides, we get a heat of also 0.5 joules. Just before we move on, I want to name 2 more processes that you might see. If you ever find out through the ideal gas law or somewhere in the problem that your temperature does not change, delta T equals 0, then you have an isothermal process. Alternatively, if you find the change in heat is 0, delta Q equals 0, then you have an adiabatic process. Okay, onward to heat engines. What are heat engines? Well, they look sort of like this. What's going to happen is you're going to have a hot area, and the heat engine is going to take some heat. Some of it's going to go to some process over here, and all the rest that it can't use is going to go to a cold source. Now, ideally, the heat engine is going to take heat from the hot source and use all of it in some specific process, so the waste is going to be dumped at the cold source, and the waste would ideally be 0. However, this is simply not true, owing to random processes, so on and so forth. Not all the energy it takes from the hot source is going to be usable. We can calculate the efficiency of a heat engine if we take the heat that it takes from the hot source, subtract the heat that goes to the cold source, and divide by the heat that it takes from the hot source. This is going to be a percentage. So let's say that our heat engine takes 100 joules from the hot source. is able to use 75 of those joules, but dumps another 25 joules into the cold source because that's unusable. Well, what's our efficiency? Equivalent to, it takes 100 joules from the hot source minus 25 joules that go to the cold source over 100 joules total. We have 75 joules on top, 100 joules on the bottom, and so we have 75. What are the units on that? There are no units. Joules and joules cancel out. So this is actually going to be a percentage. I mean, 75 over 100 is 0.75. But yeah, just convert that into a percentage and you have a heat engine with a certain efficiency. In this case, we have 75%. Alright, to recap. You can stick gas in a system where it has a piston on top. If the gas expands, its volume increases, then it's going to do work on the piston. If the gas contracts, then the piston is doing work on the gas. We can calculate the work done by a piston gas system through the equation work equals pressure times the change in volume, where pressure is in pascals and volume is in meters cubed. However, this can only be used when your pressure is constant, so more usefully go to a pressure volume chart and just find the area under each specific line. Note, of course, that you're doing positive work if the volume increases and negative work if the volume decreases. You can also use the equation to find the internal energy of a system. Delta U equals Q minus W, where delta U is the change in internal energy, Q is the heat, and W is the work. Note that for a closed set of processes, that is, on a chart all the lines are connected to each other, the change in internal energy is going to be 0. For a process in which the volume does not change, it's called isovolumetric. If the pressure doesn't change, it's called isobaric. If the temperature doesn't change, it's isothermal, and if the heat doesn't change, it's adiabatic. On to heat engines. You're going to have a heat engine that is situated between a hot and a cold source. It's going to take energy from the hot source and use it to do some process, and all the energy it can't use is going to be dumped to the cold source. The efficiency of a heat engine is the energy taken from the hot source minus the energy that goes to the cold source divided by the energy taken from the hot source, and then just convert that to a percentage. Alright, that's all for now. Again, I'm Brian Creer. See you next time.